Well, thank you for that warm welcome, Taft, and thank you all for coming. I realize that my title today is a bit provocative. Let me see if this works. Okay. How stars destroyed the atoms in the universe. Obviously, the stars didn't destroy all of the atoms in the universe. We are made of atoms. We're breathing atoms now. This building is made of atoms. So a few lucky atoms survived, fortunately for us. But the vast majority of them have long been destroyed 13 billion years ago. And we actually understand very little of this process. And as you can imagine, when you destroy almost everything in the universe, it has some implications for what happened to the universe afterwards. So I'm going to try to address this issue and tell you how we're using Keck and the Hubble Space Telescope both in conjunction to understand this process a little better. So here's a snapshot of what the universe looked like 13 billion years ago. It's pretty boring. The gas was kind of uniformly distributed with slight overdensities in certain regions, which are obvious here. But that's it. There were no stars, there were no galaxies, no planets, no people. But eventually, this gas and the dense regions here are going to start coalescing with gravity, attracting each other, and coalescing into the first stars, which are going to coalesce into groups of stars, and then galaxies, and then into the universe we see today. I actually have a nice movie to show you just that. This is not my movie, but some theorists at the University of California at Santa Cruz have created this. And this is that same picture of that initial gas and how it was distributed in the early universe. And I'm going to play a movie, and it's going to actually go pretty quickly, unfortunately, but you can see how it coalesces into the galaxies we know today. So this is starting a little over 13 billion years ago, okay? Now the universe is expanding, and this gas coalesces into many, many small groups of stars, which then coalesce into a gigantic galaxy here in the center. And this galaxy, we are stopping here about 10 billion years ago, so you've seen 3 billion years of evolution. This galaxy here will eventually turn into something very similar to what our Milky Way galaxy looks like today. So I'll just play that one more time. As you can see, it gets quite messy. But what I can tell you is the vast majority of the gas and the atoms that we saw in that initial configuration have long been destroyed. So this is a story of atoms, and you're probably all horrified because you remember this from your intro, chemistry classes in high school. But I'm here to, can you see this pointer at all? Yeah? Okay, fine, I'll leave this. I'm here to tell you that it's actually much simpler than this. We don't have to deal with all of these elements. In the early universe, all of these elements didn't exist, okay? So that's why actually, in some senses, looking further and further back in time, things get a lot easier. Atoms in the early universe, this periodic table looked very different, right? This is the periodic table of the elements 13 billion years ago, 13.5 billion years ago. Better, right? Now we can start to understand this, and actually, this is hydrogen, helium, lithium, and beryllium. Lithium and beryllium actually are barely there in just trace amounts, 1 in a million, 1 in 10 million atoms. So we can ignore those. Now it's getting even easier. All we've got is hydrogen and helium. Great, okay? So now we can understand this a lot easier. And 9 out of 10 actually of these atoms are hydrogen in the beginning of the universe. Almost nothing is helium. The other 10% is helium. So really, we can just focus on the hydrogen, because almost everything is hydrogen in the early universe, okay? And to remind you, what is a hydrogen atom and what's a helium atom? Fortunately, not only are there fewer atoms, but these are the simplest possible atoms that exist, okay? Hydrogen atom is the simplest one with just a positively charged proton and a negatively charged electron, with that negatively charged electron orbiting around that proton. They're attracted because opposite charges attract, and so much like the moon is attracted to the Earth, and is orbiting around the Earth. This electron is orbiting around this proton, okay? Very, very simple. The helium atom's a little more complicated. There's 2 protons, 2 neutrons in the center, in the nucleus of the atom, and 2 electrons around it. So we're going to ignore helium for the rest of the talk. Just talk about this one atom. The universe is made of almost all hydrogen in the beginning, and that's all it is, a proton, a nucleus that is 1 proton and 1 electron orbiting it, okay? Now, I said destroyed the atoms. The stars destroyed the atoms in the universe. What I mean by that is when we take this electron away from that proton, it no longer acts like a normal hydrogen atom. It interacts with other matter and other light completely differently, okay? So when I say destruction of the atom, I'm just talking about removing the electron away from the proton. So how do we do that? Much like if we have something orbiting the Earth, if we give it more energy, it will move further away from the Earth. If we give it enough energy, it'll completely escape from the Earth. And the same thing goes with an electron. If we give it enough energy, it can escape from this proton. They're attracted to each other, but we give it enough energy and we can pull it apart. So how do we impart energy on this electron? The answer is with light. If we hit it with some light, with enough energy, we can just strip this electron away. Now, light comes in a lot of different colors, as you know, and only some of that light is capable of stripping this electron away. The light you're familiar with, visible light to us, we see from red to violet, and the rainbow of light that we can see with our eyes. But of course, there's a lot of other light, it has each different type of light has a different amount of energy, which is dictated by its wavelength. All it is just an electromagnetic field that's oscillating back and forth. And they have different, so it's basically just a wave, and the length of that wave dictates how much energy is in that light. So very low energy light, radio waves. These are wavelengths like this big, okay? Microwaves, like what your cell phones use, are much smaller. Then you get to infrared light, it's even smaller. And then eventually we get to the light we know and love and we can see, right? Red light, orange light, to blue light, and then to violet. And this is going from less energetic to more energetic light, okay? But when we get beyond violet, it becomes ultraviolet light, right? You've all heard of this, and then if you go beyond ultraviolet light, you get X-ray and even gamma rays, okay? Very, very energetic light here. And it turns out that none of this here can harm the hydrogen atom. It doesn't have enough energy at all, okay? Even violet light, it doesn't do it. What we need is just past that. We need ultraviolet light. And it's the ultraviolet light that we care about, because that's the only light that it has energy enough to destroy the hydrogen atom, okay? It turns out stars produce light of a variety of colors. And I'm showing this example because it's probably one of the most famous constellations. You can see it nicely here from Hawaii, in the winter months especially. And it shows a nice juxtaposition of 2 different types of stars that produce very different colors of light. Very red light, very blue light. And what dictates that? It's kind of a complicated plot, but I'll take a minute to explain it. This is a plot that shows how bright stars are on this axis. So the brighter they are, the higher they're going to be up here. And the hotter the star is, it's going to be more to the left, okay? And almost all the stars in the universe lie right here on this diagonal. The low mass stars, very, very small stars, are down here. They're very cool, and they're extremely faint. And they don't put out a lot of energy, so I don't personally care that much about them. There are some people studying them very hard. But actually, most of the stars in the universe are like this, okay? But they don't actually produce a lot of energy. On the other end, however, these are rare stars. There's not many of them out there. But these things are extremely hot, extremely massive, and extremely luminous, up to 1 billion times more luminous than these very low-mass stars. Okay? These produce predominantly red light. As you get to more and more massive stars, they shift in what type of light they produce. Over here, you're producing mostly blue light. And when you get to even more massive stars, actually the majority of the light we can't even see. It's produced in the ultraviolet. This is the type of light that can destroy the hydrogen atoms, okay? So these are the only things we care about when we're talking about destruction of the hydrogen atoms. We don't care about these things. They're boring. We're going to only talk about these very, very massive, rare, extremely luminous and energetic stars. By the way, the sun is here. It's your average star. It's right in the middle. So let's go back to Orion. This is Betelgeuse. It's a red star. It's very, very cool. And it's not producing ultraviolet light at all, okay? It's too cool. This is Rigel, an extremely luminous, extremely hot star, similar to the type of star that we care about, okay? The type of star that can produce enough ultraviolet light to actually destroy gas around it. Now, there's one thing about these types of stars that I haven't mentioned yet, and it's really important. And that's how long these stars last, okay? These stars, they're all bright because they're burning their fuel, right? They're fusing atoms together in their cores. These do that very slowly. That's why they don't produce a lot of energy. That's why they're not very bright. These are incredibly efficient at it, and that's why they're so bright. But because of it, they run out of their fuel incredibly fast, and they only last for a very short amount of time. Only a few million years, actually. Okay, a few million years is a long time to us, but in terms of the age of the universe, that's nothing. It's like just a flash in the pan, basically. These things here last 20 billion years. So in comparison, a few million is, a fraction of a percent of that. So that's really important because when you form a group of stars, you'll form a little bit of everything. And the only ones that can produce the ultraviolet light to destroy the atoms aren't going to be around very long. They run out of fuel extremely fast. So, when you look at a young star-forming region, you'll have a little bit of everything. You'll have these low-mass stars, these high-mass stars, but what will dominate is these things for a while. Okay? So when you look at a new group of stars, like this one here, there's thousands and thousands of stars, but what do you notice? You notice the 10 or so really, really bright ones, and they're really blue, and they are emitting a huge amount of ultraviolet light. And I like this, this picture is perfect for this talk because it kind of shows everything I want to convey about these bright stars. You create new stars, and only these 6 or 7 really bright stars produce the ultraviolet light. And you can actually see its effect on the gas around it. You can see the destruction of the atoms. That's what this glow is here. It's emitting ultraviolet light in all directions. And this glow is actually the result of the destruction of the atoms. So you're actually seeing that out here everything's fine. But in here, nearby these stars, all of the atoms in here are completely destroyed. The electrons have been stripped away because of the ultraviolet light from a handful of stars in this central region. Now, this is just some very small star-forming region in a galaxy very close to us. So this is nice, but I want to see we want to know how this happened to the entire universe, okay? This is some, nothing small scale. This happened to the entire universe, but we don't know really how it happened. So here's kind of a history of the universe from the Big Bang is on the very left, and the universe today is on the right, okay? The atoms formed very early on. So we're left with all hydrogen atoms here, and then nothing happens for a while. The first stars don't form for a few 100 million years. But eventually these first stars form, and they produce ultraviolet light, and they destroy these little pockets around them. And more of these stars start to form, eventually have whole galaxies of them. And the destroyed regions begin to overlap. And then 1 billion years after the Big Bang, this is 13 billion years ago, all of the gas between the galaxies, most of the gas in the universe, has now been destroyed because of that ultraviolet light. And the really important thing is, for the next 13 billion years afterwards, it's remained that way. These atoms have remained stripped apart for almost 13 billion years. The problem is we don't know how that happened. Here's a movie, a simulation of how that might have possibly happened. This is a simulation of a huge volume of the universe. And wherever it's black is where the hydrogen is intact. But there's these little galaxies inside of it that are going to start to emit ultraviolet light and destroy regions around it. And you'll see those regions spread out and multiply. So I'll run this movie. And you can see these cavities being opened up where the atoms are being destroyed, the hydrogen's being destroyed. This is a cube that's rotating, by the way. And you can see there's more and more of these cavities, and they're beginning to spread and overlap as more and more stars begin to form and produce more and more ultraviolet light. And this is actually happening pretty quickly relative to the age of the universe. And right at the end, there's a huge transition where we go from a lot of hydrogen and black here to nothing. This is the end. 1 billion years after the Big Bang, all of those atoms have been destroyed now. And all that's left is the gas that's inside the galaxies, which is actually a small minority of it. But it's important, that's what we are. So, this movie, this simulation, makes it look like we know how it happened. But we don't. We're just guessing here. We don't know a lot of things about this process. What we need to know, basically, the one important question is there enough ultraviolet light? We need enough ultraviolet light to destroy every single atom in the universe. Is there enough? So there are two important points that we need to answer to address this question. One, how many ultraviolet bright stars were there in the universe? If we know that, we know how much light there was. We know if there's enough to destroy all the atoms in the universe. And the second one is important, but not a lot of people consider it. What fraction of that ultraviolet light produced by these stars actually escapes the galaxies? Remember, almost all of the gas and all of the atoms are outside of the galaxies. So if we're going to destroy those, that ultraviolet light that's produced by the stars in the galaxies actually has to escape those galaxies. And that process, we don't know how that happens. And that's what a lot of my research is on, and that's what the rest of the talk is basically going to be about. I will address this, however, in a couple of slides, actually in one slide. How do we know how many ultraviolet bright stars there are in the universe? Well, I will make that there are many people in the Keck community that are studying this in exquisite detail because this is obviously very important. This is basically when and where did all of the stars in the universe form. I'll just sum it up in one picture. This is how we do it. We have to count the stars, basically. And in order to do it, we have to take a very deep image of the universe. This is, I think, the most beautiful image ever taken. It's definitely the most expensive image ever taken. This is a picture from the Hubble Space Telescope. And here's what went into this image. When you're taking a picture with your camera and it's faint and there's not a lot of light, you have to take a long exposure, right? You have to open the shutter and let more light come in than you normally would. So instead of taking a 50th of a second, you take a 10th of a second exposure, maybe even a second if it's really faint, right? We did the same thing. We pointed at a piece of the sky, and we left the shutter open on the camera on the Hubble Space Telescope but not for a 50th of a second or a second, or an hour, or a day, or a week, or a month. This is several months leaving that shutter open. Close it up, analyze the data, this is what we get. Now, keep in mind, this is a very, very small piece of the sky. If you were to take a penny and hold it at arm's length, that would be a heck of a lot bigger than this. It's actually, you thought I was going to be comparing it to the penny. It's actually the eye on Abraham Lincoln. And the other cool thing about this image is that these aren't stars in our galaxy, right? These are completely whole other galaxies. Every single dot you see here is an entire other galaxy with hundreds of billions of stars and probably hundreds of billions of planets in it. Every single thing, except this, that, and that. Everything else. So literally trillions of stars in this single image. And this is how we determine how many stars there are in the universe. We can see how many galaxies there are, we can see how bright they are, and we can see what colors they are. So we know what types of stars are contributing, right? You can see there are redder galaxies, there are very blue galaxies. There's a huge variety of luminosities, how bright these are, and what colors they are. And when we count this all up, we can infer how many of each type of star there is in the universe. So there are many people working on that. I'm working on that as well, but this is not what I'm here to talk to you about today. But I will answer this question for you. There are plenty of ultraviolet bright stars in the universe. Okay? 5 to 10 times more than what's necessary to destroy the hydrogen atoms. So we're pretty confident about that. That's great. But the problem is, what fraction of that light actually escaped the galaxies? That is the big unknown, the big mystery, because we would expect that nothing could escape. And here's why. This is that same image I showed you of the young star cluster destroying the gas around it in this little sphere here. But notice, this area, this area, this area, this is fine. The gas is totally intact. It's not destroyed at all. And it's being untouched by these stars here. Why is that? These stars still exist. They're spewing out a lot of ultraviolet light. Why doesn't this region of destroyed gas move out further and further and continue its destruction? The answer is these pesky hydrogen atoms recombine. You try to strip them away, and they attract back to each other and recombine. And now we've wasted our ultraviolet light. We use the ultraviolet light to destroy the atom, and it recombines and says, what else you got? So this is inside a galaxy, right? And so in order for this to affect and destroy the atoms outside of the galaxy, which is what we care about, that's where most of the atoms in the universe are, this light has to get past all of this gas somehow without interacting with this gas, and instead move out of the galaxy and interact with the gas outside of it. And this is just a demonstration of why these atoms recombine. If you've got a whole bunch of destroyed atoms around you, and you have an intact hydrogen atom here, and you hit it with some light, and you strip that electron away, and it zips off in this direction, oh look, it's going to run into another proton right away. They're attracted to each other, and they'll recombine into hydrogen. And now you've wasted your ultraviolet photon, your ultraviolet light, and you still have the same amount of hydrogen atoms that you had before. This is in a galaxy where there's a lot of atoms. This will happen in a split second. It'll find another one, laugh it off, and that's it. Outside of the galaxies, there's a lot of space, and the density is extraordinarily low. And if you strip this electron off, it will not interact with another proton, likely for tens of millions of years. So when you destroy an atom or hundreds of millions of years, actually. So if you destroy a hydrogen atom in the space between the galaxies, it's for good. Whereas in the galaxy, it's not at all. So this is the star-forming region that I've been showing you repeatedly. That's actually a very small portion of a galaxy, right? And that whole galaxy is filled with gas that ultraviolet light can interact with. Somehow, this ultraviolet light has to get past all of this gas and out into the intergalactic space. So how are we going to do that? How do we move this gas out of the way and allow some of this ultraviolet light to escape? There's a lot of different theories, and this is what we don't know. But the one thing that we can say is these very bright stars, when they run out of their fuel, they blow up. And we call that a supernova. And when they do, it's pretty catastrophic. They input a huge amount of energy into the galaxy that they've formed in, and they can push that gas around in many different ways. Okay, so here's actually a simulation of that. This is a fake galaxy here in a computer simulation, and we're going to have stars in the very center that blow up. Okay, and there'll be repeated explosions from lots and lots of stars. And here's a simulation of what happens to the gas in that galaxy. There they go. These little cavities open up, but it keeps happening. And eventually, these cavities reach the edge of the gas disk, and it's completely destroyed part of the galaxy. Now, if you've got stars here emitting ultraviolet light, they can get out. The light can go in this direction where there's not a lot of gas anymore. It's been pushed out of the way. Here, there's still a lot of gas. Here, still a lot of gas. But certain lines of sight are free and clear, okay? And as you know, as I told you, there's more than enough ultraviolet light. We just need a small fraction of it to escape. And maybe this is how it happens. We know these winds of gas are coming off of star-forming galaxies. This type of disruption of the gas in a galaxy is happening all the time. So maybe this is how the ultraviolet light escapes. Now, there are other ways. And it happens that this is another cool movie I can show, so I've decided to show it. This is galaxies actually collide with each other all the time. And in the early universe, the universe was much smaller, so they collided a lot more often. And actually, when that happens, the stars and the gas move very differently from one another. And so you can get stars that are completely separated from the gas, which is what we want, right? So here's a simulation of two galaxies colliding. The stars we care about are the blue ones. These are new stars, young stars. So you can see them here, actually really nicely. It's a good projector. Here's another galaxy that's about to run into. And when it does, it actually induces new stars to be formed. You'll see them in blue popping up. New stars created. Now notice where the blue stars are. Sometimes very far away from the center of the galaxy, way out here, way out here. Most of the gas is in the central region. And so maybe this collision of galaxies is able to move some of these ultraviolet bright stars outside of the centers of the galaxy where all that gas is, and then some of that ultraviolet light is able to escape. And eventually these things coalesce into one galaxy. So these are two scenarios. Which one is it? Is it both? Just one? What's the dominant mechanism that allows this ultraviolet light to escape? This is what I'm trying to find out. So how are we going to find this out? Well, we're going to use the two biggest observatories, two best observatories in the world. Okay? The Keck telescopes, which you know and love and can see from here on a clear day. And the Hubble Space Telescope, which is actually orbiting the Earth. For what we want to do, these two telescopes are by far the best in the world, or out of this world, for what I want to do, okay? For detecting this ultraviolet light. Remember, I showed you this beautiful image of all of these extremely faint, distant galaxies. What we want to know now is we want to try to detect that ultraviolet light escaping, directly detect it. This is visible light, right? Red, blue light. What we want to look at is ultraviolet light coming from these same galaxies. And if we detect it, we can determine what fraction of it is actually coming out, and determine if that's enough to have destroyed the atoms in the universe. So we did just that. This is actually a collaborator of mine, Alice Shapley, who's a professor at UCLA. She used the Keck telescopes, and in perfect conditions, with a couple of nights staring at one pointing, she stared at those distant galaxies. And those distant galaxies, the very distant ones, are marked in red and blue. And you can actually see there's a few of them that are detected. That one there, this one up here, there's one other one. This one here. That there's actually some light, there's some signal, it's very, very faint. But this has never been detected before, ever. Okay? And a few of these actually have ultraviolet light coming from them. It's the first time this has ever been detected coming from a galaxy. And here's a close-up. This is the ultraviolet image from Keck. This is in black here is the visible light. This is just red light, basically, that you can see with your eye. This is an entire galaxy. It's very distant and very small, so we can't really see much detail. But then this is the ultraviolet image, just a little dot. It's extremely faint. This is very difficult. Nobody's ever detected this before, okay? And this is that light that's capable of destroying hydrogen. And now if you overlay where this is emitted from this galaxy, that's what these contours are in green. So this is the galaxy here where we can see light of other energies, but the ultraviolet light is only coming out from what looks like a small part of the galaxy. That's really interesting. It's not actually coming from the entire galaxy. So what the heck is going on? Is this some galaxy collision? Is it that there are supernovae here that are disrupting the gas? Which one of these mechanisms is acting here? Unfortunately, this image doesn't have high enough resolution to see what's happening, okay? So we went to Hubble and asked for a whole lot of time on Hubble. They normally don't do this, but we asked for 32 orbits of Hubble. Normally they give out allotments of, oh, you want to look at this galaxy, you get 4 or 5 orbits. And we got 32 orbits. This is the deepest image in the ultraviolet that's ever been taken anywhere. And we targeted the galaxies that the Keck telescope found. So this is the comparison of the two images. This is Keck on the right, Hubble on the left. Hubble looks pretty good, but this is not to disparage Keck. Keck is much, much faster at detecting these galaxies than Hubble is. And Hubble cost 100 times as much. So, yes, Hubble's very good, but it's also very expensive. But nonetheless, you can see why it's important too, right? Keck is very efficient at finding these galaxies. We don't want to point Hubble blindly. It's way, way, way too expensive. So Keck was able to find out where these galaxies were that were emitting this ultraviolet light, and then we could go and point Hubble in that same direction. And you can see the benefits, right? You see exquisite detail in these galaxies. So this is that previous image that we got a glimpse of this new emission from Keck. Now we're going to zoom in on this part because we have better resolution. And this is what we see with Hubble here. This is the visible light image. It's actually not one galaxy. It's 2. And in the ultraviolet, it's all coming from this smaller, fainter galaxy, which is very interesting because remember I pointed to 2 scenarios that could allow this ultraviolet light to escape, right? And this looks a lot like one of them. So, is this possible evidence that this is a collision of two galaxies that's causing this ultraviolet light to escape from this fainter galaxy here? It certainly looks like it. Now, this is where Keck comes back into play, because the only way we can make sure that this is a collision is to go back with Keck and see if these galaxies have the right, if they're nearby each other. We can look at their different velocities to see if they're actually interacting or not. Can't do that with Hubble. We have to do it with Keck. And we're actually doing that now. But this is certainly indicative of collisions causing this ultraviolet light to escape. So maybe these collisions, which were much, much more common in the early universe, are the reason this light is escaping. So our previous question was, how many ultraviolet bright stars? There's plenty. Now, what fraction of that light is coming out? We have an estimate. It's maybe 10 or 20%. So if we have 10 times as much as we need and 10% is coming out, we have just enough light. Just barely. But actually, that's by definition, because we're taking into account how fast this transition happened. It should exactly equal just enough. So this is very promising. But there's a lot more work to do. Every time we detected a galaxy with Keck, in this ultraviolet light, it was a faint galaxy. It was not these bright, vigorously star-forming galaxies. It was these little baby galaxies. And remember this image from the simulation I showed. This is the big galaxy. There's a whole lot of these little faint galaxies. And it seems like that's where all the ultraviolet light is coming from, which is really annoying because they're really hard to study, right? These things are so bright, we just detect them in 10 minutes with Keck. These things are 10, 20 times fainter. It's very, very difficult to study these things in detail. The universe is conspiring against me. So, how do we study these faint galaxies when it takes, many days with one image with Keck or Hubble to detect these things? If we need to study things that are 10 times fainter, it'll take years. We can't do that. Fortunately, nature has provided something that can help us out. If there were some way to just magnify these galaxies to make them brighter, then we could study them no problem, right? Well, turns out there is a magnifying glass in the universe. There are many of them. We're going to use something called gravitational lensing. Einstein predicted a century ago that matter can actually bend light. If gravity is strong enough, it can actually make light bend. And there are lots of places in the universe that have a lot of gravity. If you put a whole bunch of galaxies in one small space, they have so much mass and the gravitational force is so strong that they can deflect a light very significantly from a galaxy's light that's traveling by it, and it'll deflect it. And this light that's coming over here will be deflected, and it can deflect the light that's going in a bunch of different directions that would never hit our telescope and focus it all towards us. It's just like a magnifying glass. And here is an image of the best magnifying glass in the universe. This is a cluster of galaxies. Every one of these yellow galaxies, is part of this cluster, this group of galaxies. It's one of the most massive clusters of galaxies in the universe, one of the most massive structures in the universe. And each one of these blue little stretched out things that you see is a galaxy that is being magnified by this cluster. This little blue thing, this one. You can see there's all of these little arcs. This long one here, this one here. And these up here, these are all magnified 10 to 100 times brighter than they normally would be if we took that cluster of galaxies away. So this is the next frontier. This is the only way we're going to be able to study these without having bigger telescopes. And it looks like we might just have detected them. Here are two of these very, very strongly magnified galaxies, and one of them, it appears that we actually are detecting that ultraviolet light coming out. so we can really get a complete census of where that ultraviolet light is coming from. So this is actually pretty new data. But ultimately, we'd like to study these galaxies in detail. Why is light coming out of that, ultraviolet light coming out of that, and not that, right? In order to do that, we need the next generation of telescopes. We've been using Keck and Hubble, but the next generation are going to blow this open, right? The next generation of telescopes will allow us to study these in exquisite detail. So the next generation Hubble telescope is called the James Webb Space Telescope. And the next generation, the successor to the Keck telescope, will be the 30-meter telescope, which will be here on Mauna Kea. And these two are designed for precisely this type of study, to study the very distant galaxies, these very small galaxies. So these little faint galaxies that we see here will be much, much clearer. And then we can know exactly what parts of these galaxies are forming stars, where the ultraviolet bright stars are, and how much of it's coming out. A lot easier. And I mean, I like to show this whenever I can. This is a rendition, a rendering of what the 30-meter telescope will look like, obviously without a dome over it. This is made of 500 mirrors, each about the size of a person, stitched together and controlled by computers so that the shape is perfectly parabolic. And to give you scale, that's a person there. So it will be pretty incredible. So we'll have a lot more to say about how these first galaxies destroy the atoms in the universe in the near future. So stay tuned. That's it. Thanks.